When you look at a chemical equation, it's kind of like you're only seeing the before and after photos of a huge event. But what about everything that happens in between? What's the real story of how these molecules actually break up, find new partners, and create something totally new? Well, that's exactly what we're going to unpack today.
So what is it? Is it just some kind of molecular magic show where reactants just poof and turn into products? Or is it something a little more like a predictable, carefully choreographed dance? Well, I'll tell you, it is absolutely a dance, one with very specific steps, partners, and an energy that we can actually map out and understand. So let's dive in.
Here's what we've got on the agenda. First, we're going to look beyond that simple A plus B equals C equation. Then, we'll introduce the two main characters that show up in pretty much every organic reaction. After that, we'll follow the steps of their incredible electron dance, map out the energy journey they take, and finally, we'll put it all together to tell one complete reaction story.
All right, part one, beyond the equation. Because, let's be honest, a simple chemical formula gives us the starting line and the finish line, but it totally hides the entire race in between.
Yeah, we see this all the time, right? A plus B gives you C. It's neat, it's clean, but it leaves out the best part. The real question, the one that drives chemists crazy, is how. Seriously, how do those molecules actually get close, break their old bonds, and build brand new ones to become something completely different?
So, really get that how, we have to meet the main characters in our chemical story. And in organic chemistry, almost every single reaction is driven by the interaction between two very different personalities, let's call it.
Okay, first up, meet the nucleophile. The name literally means nucleus-loving, which totally makes sense because the nucleus of an atom is positive, right? A nucleophile is rich in electrons. It has this pair of electrons just sitting there, ready and willing to go out and make a new bond. Just think of it as the generous electron giver in our little drama.
And of course, for every giver, there's got to be a taker. So say hello to the electrophile. Its name means electron-loving. This molecule is the opposite. It's electron-poor. It's got this empty space, an empty orbital, and it is actively looking for a pair of electrons to fill it and become stable. This is our electron taker.
And when you see them side by side like this, the whole opposites attract story just clicks. You've got the electron-rich nucleophile and the electron-poor electrophile. One has electrons to give, the other has a space to accept them. It's this fundamental attraction that literally sparks the whole chemical reaction into life.
So we've got our characters. Now, what about the plot? Well, in chemistry, we call the plot the reaction mechanism. This is the step-by-step choreography of the electrons. It's the playbook that tells us exactly how the reaction unfolds, move by move.
And the language we use to write out this dance is the curved arrow, or the pushed arrow. And this is so important. An arrow always starts from where the electrons are, our nucleophile, and it points to where the electrons are going, our electrophile. It's the universal symbol for making and breaking bonds in chemistry.
Let's actually watch this dance with a simple hydrolysis reaction. Okay, step one. Our nucleophile, which is a water molecule here, attacks the electron-poor carbon atom. See that first arrow? It shows the electron pair from the oxygen reaching out to form a new bond with that carbon. Now, carbon can't have 5 bonds, so to make room, the electrons in the double bond get pushed up onto the other oxygen. That's what the second arrow is showing.
Now, that initial attack creates this unstable, high-energy molecule called an intermediate, and molecules do not like to hang out in this state for long. So in step 2, after a quick proton gets shuffled around, those electrons collapse back down, reforming the double bond and kicking out another part of the molecule. The final arrows show this whole rearrangement, and boom, we have our stable, final products. The dance is complete.
Okay, so we have the characters and we have their dance moves, but what about the dance floor? Or maybe a better way to think about it is the terrain. Every single chemical reaction has this energy landscape it has to travel through, with hills to climb and valleys to rest in. This energy map is the next critical piece of our story. And this is the map we use. It's called a reaction coordinate diagram. And I know it might look a little intimidating, but it's actually pretty simple. The vertical axis, going up and down, that's potential energy. The higher up you are, the more unstable the molecule is. The horizontal axis, left to right, is just the progress of the reaction, from start to finish.
Now, the most important part of this whole map is that big hill in the middle. See, reactants don't just magically turn into products. They have to climb that hill first. The very peak of that hill is called the transition state. It's the highest energy, most unstable point in the entire reaction. And the height of that hill, that's the activation energy. It's the bare minimum amount of energy you have to put in to get the reaction to even start.
And this just brilliantly shows us the speed or the kinetics of a reaction. A reaction with a really high activation energy, that's like trying to push a giant boulder up a steep mountain. It's going to be slow, it's going to take a lot of effort. But a reaction with a low activation energy, that's like stepping over a small curb on the sidewalk. It can happen way faster and a whole lot easier.
All right, it is time. Let's put all the pieces together. We've got the characters, we've got the dance moves, and we've got the energy map. Now we can combine them to tell the complete, unabridged story of a chemical reaction.
Okay, let's watch it all happen with a reaction called a nucleophilic acyl substitution. First, let's identify the characters. On the left, we've got our electron-rich nucleophile, and it's meeting our electron-poor electrophile. Second, let's follow the dance. That first arrow shows the nucleophile attacking the carbon, pushing electrons to form that new bond. This creates that high-energy intermediate you see in the middle. And finally, look at the map below. The diagram shows this exact journey. We start with our reactance energy, we climb that activation energy hill to the top, and then we drop down in energy to form our final, more stable product. See? The characters, the dance, and the map, they all tell one single, complete story.
So you see, a chemical reaction is never just some boring equation. It's a dynamic story. It's got characters, a detailed plot, and an entire energy landscape. And when you understand these things, chemistry transforms from just a list of facts you have to memorize into this incredibly powerful tool for predicting and even creating things. Which really leaves us with one final thought. Now that you know how to read these stories, what amazing new stories can we write?